Hello. We will continue our learning actually about eigenvalues and eigenvectors of n by n matrices. Okay, so after fundamental theorem of linear algebra version 3, now we have this theorem and we will just see solve two problems related to this theorem. And after that, we have another two theorems and finish this section of the chapter. Anyway, this theorem states that if A is a square matrix with eigenvalue lambda and corresponding eigenvector x, it says that for any positive integer n, lambda to the power of n is an eigenvalue of A to the power of n with corresponding eigenvector x. And the second fact is that if A is invertible, then 1 over lambda is an eigenvalue of A to the power, actually A inverse with corresponding eigenvector x. The third one is if A is invertible, then for any integer n, A to the power of n is an eigenvalue of A to the power of n with corresponding eigenvector of x. Okay, let's start with the first one. Here, we will actually make use of mathematical induction method to prove this one. Here it says that for any positive integer n. So this n is 1, 2, 3, or n of these numbers. And also it's given here that, let me just write here, it says that square matrix with eigenvalue lambda and corresponding eigenvector x. So we are talking about this equation, such for matrix, right, and lambda x. So we know this A, we know this lambda. Now from here we are saying that here then if you want to find actually the eigenvector of A to the power n times x, and what is the eigenvalue of A to the power of n? Here is saying that then you don't have to calculate, actually raise this matrix A to the power of n after the multiply by x and solve the equation. It's just saying that then its eigenvalue is just lambda to the power of n x. So its eigenvalue is A to the power of n. So now when n equals 1, right, when n equals 1, it is true. And n equals 1, here we have A to the power x, I mean, A times vector x equals lambda to the power of 1, it's just lambda times x. And all already is given, right? It's a fact, actually. It is true. So now we actually suppose that we assume that for some positive integer k, and also this is true. Let's say it is true, A to the power k times vector x equals lambda to the power of k times vector x. Now here we are assuming that also for some positive k, the eigenvalue of A to the power of k is lambda to the power of k. Now I will show that also for the next one, if n equals k plus 1, and also it will show that actually its eigenvalue of A to the power k plus 1 will be lambda to the power of k plus 1. To show this one, let's continue from here. So here we have A to the power of k plus 1 vector x, right? And by using the definition of the power of matrix, we can just write it as A times A to the power of k, and here we have vector x. And this is given from the previous hypothesis, right? And here from the previous assumption, so here we have A. What is A to the power k times vector x? It's just equal to lambda to the power of k, and here we have vector x. And by using the property of matrix, this lambda to the power of k is just a scalar. We can just take this out. I can write it as lambda to the power of k. Here we have matrix A, and here we have vector x. And also we know that this matrix A times vector x, that's equal to lambda times x. So here we have lambda to the power of k times lambda, and here we have vector x, which is equal to lambda to the power of k plus 1 times vector x. So since also for the next one, the same thing works here, that means that by induction, the result is true for all integers that is greater than or equal to 1. Okay, that's the proof of the first part. How about B? For B, it says that if A is invertible, then 1 over lambda is an eigenvalue of A inverse with corresponding eigenvector X. Okay, so A is invertible, and we know that this A times X vector, right, that's equal to lambda times vector X, right? Since A is invertible, that means that it has inverse. I can just multiply both sides by its inverse. So here we have A inverse times A vector X equals, and here we have lambda A inverse times X. And A inverse times A, that's equal to identity matrix, and identity matrix times X, vector X, just X vector, right? So what we have here is vector X is equal to lambda A inverse and the X. And also since A is invertible, right, we know that determinant of A is not equal to 0. It cannot be equal to 0. So that means if determinant is not equal to 0, this lambda cannot be equal to 0 because it should be different from 0. That's actually, we have just seen that theorem in the previous video. So that means that since I know that lambda is not equal to 0 because of the invertibility of matrix A, so I can just divide both sides by lambda. And what we got here? Here we have A inverse times X, vector X equals 1 over lambda times vector X. So here we have some n by n matrix, and here we have a scalar, right? And it satisfies all the conditions actually given in the definition of the eigenvector and eigenvalue. That means that 1 over lambda is an eigenvalue of this matrix. What is it? It is A inverse. That is the proof of this one, the second part of the theorem. And third part, it says that if A is invertible, then for any integer n, lambda to the power of n is an eigenvalue of A to the power of n with corresponding eigenvector x. Okay. So again, here, the first part, when n is positive, we have already proved it's here. So now we have to show that actually it works for when n is 0 or negative. Okay, part C. So first I have to show that here, eigenvector of A to the power n. Here we have, okay, this is the third part. Let me just use another color and green. Okay, third part. So we have to show that the eigenvalue of A to the power of n is just lambda to the power of n. Okay, when n is positive, we have no problem. So the first case is, how about if n equals 0? If n equals 0, here, A to the power 0, we know that A to the power 0, and here we have vector x, and here we have lambda to the power of 0, right? So that is x. And actually it's true because A to the power 0, that is identity matrix, and here we have vector x, and here we have 1 and vector x. And we know that here we have just x, right? And x, so here we have the identity matrix, its eigenvalue is 1. So number 2, how about if n is negative? If n is negative, I can just write n as something like this, minus m, where m is positive. Okay, so here we will have here, instead of n, I will write negative m minus m. So here we have A minus m times vector x. Now, I don't know what is the eigenvalue of A to the power of minus m. Let's say that thing is k. Now we are going to find this k. And here we have vector x. And by using the definition of the power of matrix, if you just multiply both sides by A to the power m, what we have here? A to the power m times A to the power of minus m, that's equal to identity matrix. So it's just here we have vector x. So here we have k times A to the power m vector x. And also we know that k is not equal to 0. I can divide both sides by k. So what do we have here then? A to the power m vector x, that's equal to 1 over k. And here we have A to the power m, right? So we know that m is positive. When it is positive, we have already proved in part A, right? If lambda is an eigenvector, eigenvalue of A, then eigenvalue of A to the power n is lambda to the power n. So that means that this is an eigenvalue of A to the power of m. which is actually this 1 over k should be equal to lambda to the power of m, where this k is equal to, just upside down, that's equal to lambda to the power of minus m, right? So that means that this lambda to the power of minus m, 1 over k, okay, no. Here, I don't have, actually, we're talking about this 1 over k. This 1 over k, that's equal to, that is equal to, okay, lambda to the power m. Okay, so we have to find k here. All right, here from here, the k equals lambda to the power of m, because we are looking for this m, right? Now 1 over k. So what is k? The k is lambda to the power of minus m, which is the eigenvalue of a to the power of minus m. Okay, that's the proof of this theorem. So immediately let's just make use of this theorem to this question. Here in this question, I'll just solve part B in the next slide. So here computes this matrix to the power of 10 times 5 over 1. And directly you can compute this, since actually we have to develop a technique to develop calculate this in a more, let's say, rigorous or mathematical way. So just apply the previous theorem to this question. So here we have, all right, solution. So let's say here our matrix A is this, 0, 1, 2, 1. And our vector is this. Here we have 5, 1. So the question here is we need to calculate this thing, right? A to the power of 10 times vector x. The question is, what is this? So to do this one, first, I don't know what is the eigenvalue of this A. Immediately, let's find the eigenvalue of A. Okay. So first, let's find the eigenvalue of A, because if I know the eigenvalue of A, how will we evaluate this? Assume that here eigenvalue of A is some kind of lambda. So then here it will be just equal to lambda to the power of 10 times x, right? Actually, this thing will be equal to, how can I evaluate this? Here, this thing, okay, will be equal to a to the power of 10 times x, right? So that thing will be equal to, if I know that the eigenvalue of a is lambda, so this will be equal to lambda to the power of 10 times vector x, just using the previous theorem. Okay, now I have no idea about this lambda, so I'll try to find this lambda. Number one, let's find a lambda. So to find a lambda, we know that we have to evaluate these determinants. Here we have a minus lambda I. Okay, this line is a bit long. So that is equal to, here we have 0, 1, 2, 1. So here we have minus lambda 1. Here we have 2, 1 minus lambda. Okay, if you just multiply minus lambda times 1 minus lambda, that is lambda squared minus lambda, and here we have minus 2. That's equal to 0. It's just a quadratic equation, and if you factorize this, here we have lambda, what is it, minus plus 1, and lambda minus 2 is equal to 0. Okay, lambda squared minus 2 lambda plus lambda is equal to negative lambda minus 2. Okay, that's correct. So here, lambda 1 is equal to negative 1, and lambda 2 is equal to 2. So now let's just find the corresponding eigenvectors. So when lambda 1 equals negative 1, the first one, what we have here? Here we have, actually we need to reduce this matrix, right? Minus 1, substitute here. Here we have 1, 1, 2, 1 minus minus 1, that's equal to 2. So reduced row echelon form of this one is just multiply the first row by negative 1 and add it to the second row. So here we have 1, 1, 0, 0. So that means that our eigenvector corresponding to this eigenvalue will be, let me just write like this. Here it will be in this form, right? It is t minus t. Any vector of this form will serve as an eigenvector for this matrix. Okay, now from here, I just need only one. So one of them is, let's say this V1 is, what is it? 1 minus 1. Okay, the second case, lambda 2 equals 2. If lambda 2 equals 2, and substituting this value into this matrix, because we are solving the homogeneous system, negative 2, here we have negative 2, 1, 2, 1 minus 2, that is minus 1, right? Again, if you just multiply 1 and add to the second row, negative 2 plus is 0, is 0, so here we have minus 2, it is 1, and here we have 0 and 0. So what we have here, we have something like this, minus 2x1 plus x2, that's equal to 0. Or x2 is equal to 2 times x1. So our vector is this form. So here we have x1 and x2, and here, what is x1? That's x1. What is x2? 2 times x1. x1 is any real number. I just need 1 here, so one eigenvector is, just put bar here, is this. It is 1, 2. As you see here, these two vectors, this v1, v2, right, they are linearly independent. That means that they span R2. So from here, as you see, this R2 is just, or can be spanned by these two vectors, v1 and v2. Why? Because they are linearly independent. Why do I need this? That means that I can express this x in terms of this v1 and v2, right? So that means that now this vector x can be expressed as the linear combination of v1 plus c2 times v2, right? Again, to find the c1 and the c2, what should we do here? As you see, just we have the system, right? Here we have something like this. Here we have vector v1, vector v2, and here we have c1 and c2. On the right-hand side, we have vector x, whose actually entries are x1 and x2. So actually, we can just write this one. So if you just put the numbers, what is v1? v1 is 1 minus 1, and v2 is 1, 2, right? And okay, 1, 2. And the third one, x, right? Also x is given. Here it is 5, 1. I'm just trying to find the c1 and c2. So if you just multiply you just add the first row to the second row. Here we have 1, 1, 5, 1. Okay, here we have 0. 1 plus 2, it is 3. 5 plus 1, it is 6. And I can multiply the second row by 1 over 3. So here we have 1, 1, 5, 0, 1, 2. And multiply the second row by negative 1 and add it to this first row. Here we have 1, 0, 3. Here we have 0, 1, 2. So that means that C1 equals 3, C2 equals 2. So here that means that this vector x can be expressed as 3 times v1 plus 2 times v2. Is it right? Yes, 3 and 2. Okay. So now, using this fact, let me get back to the question. So we need to actually evaluate that thing. 8 to the power of 10. Here we have vector x. So a to the power of 10, this vector x, I can just write it as 3 times v1 plus 2 times v2. And if you just distribute this a to the power 10 over this v1 and v2, here we have 3 times a to the power of 10 v1 plus, and here we have 2 times a to the power of 10, here we have v2. And just using the theorem, we will use that theorem here. We know that actually, what is the eigenvalue of a? It is lambda 1, right? Corresponding to v1. An eigenvalue of a corresponding to v2, that's lambda 2. So now here, I can just write here, lambda 1 to the power of 10 v1, because v1 is an eigenvector of a, plus 2 times a to the power 10, and the eigenvalue corresponding to this vector is, it is lambda 2 to the power of 10. Here we have v2. So now, if you just substitute the values here, that is 3 times, what is lambda 1? If you remember, lambda 1 is negative 1. So here we have negative 1 to the power of 10. And how about V1? V1 is 1 minus 1. So here we have 1 minus 1 plus 2 times, how about lambda 2? Lambda 2 is 2. So here we have 2 to the power of 10. And V2 is 1 and 2. Its components are 1 and 2. That's it. Now see here, we didn't have to multiply or perform any matrix of multiplication here. So what we have here we have something like this. Here we have 1, so here we have 3 and minus 3, right? And plus, we're just adding these two vectors. Here we have 2 to the power of 11. And if you add the second components, here we have 11, 12, 2 to the power of 12. And also we can evaluate this. What is 2 to the power of 11? 2 to the power of 11 equals 2048. And if you just add 3 to this, here we have equals 2051. And how about here, 2 to the power of 12? And we should just subtract 3. That's equal to 4093. Okay, that's it. So now we will actually do the second question. Just actually, how to say, so that you get used to it more. It's a similar question, just here the power is different and idea is the same. So in part B, we're going to solve that thing. Let's say matrix B. Matrix B is, here we have 1, -2, 4, -5, and our vector, let's say vector y, is 2 and 7. So again, what is the question here? The question is, we need to calculate this, right? A to the power of 20 times vector y. Actually, here I use b. So here we have b to the power of 20. So we need to evaluate this. Okay, that's the question. So all right. Okay. So, okay, to some reason it's gone. Matrix B, it is 1, -2, 4, -5, and vector Y, it is 2 and 7. So we are going to evaluate this, b to the power of 20 times vector Y. Good. As you know, actually, first we need to find the eigenvalues of this matrix. To do this one, we need to evaluate this determinant, right? This b minus lambda I. So that is 1 minus lambda, 1 minus lambda, minus 2. Here we have 4, minus 5, minus lambda. That is equal to 0. We have to solve this equation. And here we have 1 minus lambda, and here we have, okay, 1 minus lambda, and I can just take this minus out. Here we have 5 plus lambda minus -2 times 4, that's equal to minus 8. That's equal to 0. Okay, so here we have minus 1 times 5, it is 5, 1 times lambda, lambda, minus 5 lambda. So here we have minus 4 lambda, minus lambda squared, plus 8, that's equal to 0. Or lambda squared plus 4 lambda, minus 5 plus 8, that's equal to plus 3, is equal to 0. Now from here, we just factorize this. So here we have lambda 1 is equal to -1. Okay. Here we have lambda 1 equals -1, and lambda 2 equals -3, right? So -1, here we have -1 plus 1 plus negative 4, so plus 3 is equal to 0, negative 3 is 9 minus 12. Okay, so these are the eigenvalues of matrix B, right? So now we need to find the corresponding eigenvectors. So the first case, if lambda equals negative 1, if lambda equals negative 1, so here, just substitute here, 1 minus minus 1 is equal to 2 minus 2, and here we have 4 minus 5 minus minus 1, that's equal to minus 4. And if you just multiply the first row by negative 2 and add to the second row, it will be 0. And multiply the first row by 1 over 2. So here we will have 1 minus 1, 0, 0. So our eigenvector is this style, right? Here we have T, and here we have T. And I just need 1. So one eigenvector is 1 and the 1. It will serve as an eigenvector. So how about if lambda equals negative 3? If lambda equals negative 3, so our here that augmented matrix, of course here I'm not augmented actual 0 column here. Here minus 3, so here we have 1 minus minus 3, that's equal to 2 minus 2. Here we have 4 minus 5 minus minus 3. That is minus 2. Right. Is it correct? Let me just check again. So here we have 4, 1 minus minus 3. Okay. It should be 4. This should be 4. So exactly the same rows. And you can just multiply the first row by negative 1 and add it to the second row. And here we have 0 row. And multiply the first row by, let's say, 1 over 2. So here we have 2 minus 1, 0, 0. What we have here, here we have 2x1 minus x2, that's equal to 0. So that means that our vector x, let me just write, maybe, okay. Here we have eigenvector will be this way, right? X2 equals to x1. So here, if this one is S, let's say, the second one will be 2S. And I just need 1. So V2, 1 corresponding eigenvector will be, what is it? When S equals 1, here we have 1 and 2. Okay. So now, next, let's say there's a third step. So as see here, this 1, 1 and 1, 2, they are linearly independent vectors. So I can express this y as a linear combination of these two vectors. So here we have C1, V1, that is 1, 1, plus C2, and here we have V2, 1, 2, right? And that's equal to y. Our y is 2 and 7. Okay, here we have the augmented matrix 1, 1, 1, 2, 2, 7. Okay, here we have 1, 1, 2, multiplied by negative 1 and add to the second row. We have 0, minus 1 plus 2, it is 1, minus 2 plus 7, it is 5. Or, and if you just multiply the second row by negative 1 and add to the first row, here we have 1, 0, minus 5 plus 2, minus 3, 0, 1, 5. So actually C1 is negative 3 and C2 is 5. So that means that this y, right, this vector y can be expressed as minus 3. So here we have minus 3 times V1 plus 5 times V2. Or you can just check this. Let me just keep it like this. Now let's get back to our question. So we need to find that thing, right? So b to the power of 20. So step number 4, b to the power of 20 vector y. And here we have b to the power of 20, and vector y is just minus 3 times v1 plus 5 times v2. Okay, that is equal to minus 3, and here we have B20. Okay, let me just write here B20 V1 plus 5 times B is the power of 20 V2. And we know that V1 is an eigenvector of B, right? And also V2 is eigenvector of B. And using the theorem, now I can just write here minus 3 times lambda 1 to the power of 20. Here we have B1 plus 5 times lambda 2 to the power of 20. Here we have B2. That's it. Now we have to just substitute the values and evaluate this. Minus 3 times, what is lambda 1? Lambda 1 equals negative 3. I'm negative 1. So here we have negative 1 to the power of 20. How about V1? V1 is 1, 1. So it is 1 and 1 plus 5 times, what is lambda 2? It is negative 3. So it is negative 3 to the power of 20. And V2 is 1 and 2. So here we have 1 and 2 equals, so negative 1 to the power of 20 is equal to 1, and multiply this thing by negative 3. So here we have negative 3 and negative 3 plus, and how about here? Here we have it is plus because 20 is an even number. So here we have 5 times 3 to the power of 20. And here we have 2 times 5 is 10. 10 times 3 to the power of 20. Or if you just add them up together, what we have here is 5 times 3 to the power of 20 minus 3, and 10 times 3 to the power of 20 minus, okay, minus 3. Okay. And the 3 to the power 20 is quite a big number, so you can just leave it in this form. That is actually a more compact form. All right, now I'm going to finish this video by two theorems here without proof. Actually, theorem 4.19, suppose the n by n matrix A has eigenvectors v1, v2, and dot, 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 vm with corresponding eigenvalues, lambda 1, lambda 2, lambda m. So here we have, let's say, and also it says that if X is a vector in Rn, that can be expressed as a linear combination of these eigenvectors. Say this. So here we have a condition here. If X is a vector in Rn, that can be expressed. We are not sure actually. That means that it's not for every vector. If such vector exists and it's possible to express this X as a linear combination of these eigenvectors, then for any integer k, a to the power of kx equals lambda 1, c1 times lambda 1 to the power of kx, and c2 times lambda 2 to the power of k v2 plus dot dot cm times lambda m to the power of k vm. Okay. Here, proof is not so difficult, but I'll skip this. What you have to understand is, first, you should understand the condition. What is given here? This thing is given, that a v1 equals lambda 1 v1. A v2 equals lambda 2 v2. Dot, dot, dot. A vm is equal to lambda m vm. Okay. And after that, we just substitute here and using the previous theorem, and you'll get this expression. Okay, that's the last theorem, but very important, but proof is a bit long. That's why maybe I'll actually do the proof in a separate video. Let A be an m by n matrix, and let lambda 1, lambda 2, dot, 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 lambda m be distinct. They're all different eigenvalues of matrix A with corresponding eigenvectors v1, v2, dot, dot, vm. Then v1, v2, dot, dot, vm are linearly independent. So this is really important theorem, and I actually will make use of this in some problems in the future. What we have to understand here is, if you're given matrix A and it has distinct eigenvalues, this lambda 1, lambda 2, lambda m, they are all different. None of them actually, if you just pick any two, they are not equal to each other. and the corresponding eigenvectors v1, v2, vm, then these vectors actually v1, v2, vm, they are linearly independent. Okay, so that's the end of this video. See you in the next video.